In this module, you will learn to program the microcontroller on the Sci-Fi Labs development board. In this video, you will learn the basics of binary and hexadecimal number systems. You had seen an analogy earlier that the microcontroller is similar to the brain. When we humans see a dangerous animal, we tend to run away from it. We do this because our brain is programmed for this situation due to our past experiences. Similarly, a robot needs to be told what action has to be taken when it receives a particular input. Since the microcontroller is the brain of the robot, we have to program the microcontroller to take a certain action when a specific input is received. The next question would be, which language can the microcontroller understand? The microcontroller cannot understand English language, so it will not be able to comprehend simple instructions in English. The microcontroller cannot understand any of the programming languages as well that you know about, like Java, Embedded C, .NET, etc. It can only understand machine level language. But it is very tedious to write in machine level language. So it is advisable to write the code in Embedded C and then convert it into machine level language using appropriate compilers. Before you start with writing the code for your robot, let us understand the basics that are required to write a program using Embedded C. As you have seen earlier, the microcontroller understands only digital signals, so all instructions need to be in binary format, which is why it is necessary for you to understand about binary numbers. For example, to convert a decimal number 156 into binary format, divide the decimal number by 2 and note down the remainder on the right hand side. The remainders are then written in reverse order to get the binary number corresponding to the decimal number. In our program, we'll be using binary numbers corresponding to the decimal numbers up to 15. You will see why this is the case at a later stage. Like the binary number format, there exists another number format called the hexadecimal number format. For a binary system, the base is 2. That is, there are 2 digits that are used to define all the numbers in the number system. For a decimal number system, the base is 10. That is, there are 10 digits to define all the numbers in the number system, which are 0 to 9. In the hexadecimal number system, there are 16 digits that can be used to define all the numbers in that number system. The digits start from 0 and go till 9, after which the next 6 digits are defined by the alphabets A to F. In the previous video, you were introduced to the hexadecimal number system. In this video, you will learn to denote the pins and ports of a microcontroller using hexadecimal numbers. As you have learned earlier, the microcontroller that you're using has 4 ports: P0, P1, P2 and P3. Each port has 8 pins. Each pin is a digital pin with input and output function. This means that each pin can receive an input or give an output in the form of 0 or 1. The pins are referred from the right to the left. That is, the rightmost pin is referred to as pin 0, the pin next to it is referred to as pin 1, and so on until pin 7. Now, each port is separated into 2 halves, and each half has 4 pins. The 4 pins are equal to 4 bits. A combination of 4 bits is called as a nibble. The port is hence divided into 2 nibbles, a lower nibble and a higher nibble. This is done so that each nibble can be referred to using a unique hexadecimal number. As is evident, the maximum binary value that a nibble can store is 1111, which is the number 15 in decimal format, which is the alphabet F in hexadecimal format. Now look at this example. The lower nibble has 0011 as the binary values, and the higher nibble has 1010 as the binary value. The corresponding hexadecimal for the lower nibble is 3. And the corresponding hexadecimal for the higher nibble is A. You can refer to the table that we had seen earlier to verify these values. So the whole port can be represented as 0x, which is the prefix used for any hexadecimal number, followed by A3, the higher nibble and then the lower nibble. So this port is represented by 0xA3. This notation will be extensively used in programming of any microcontroller based electronics. Now let us see a few more examples. In the first case, the higher nibble is 8 and the lower nibble is 0. This port can be represented in hexadecimal format as 0x80. Similarly, do it yourself for the next few cases. It is advisable to keep the binary to hexadecimal conversion table handy while doing these operations.